Hello everyone, my name is Lara and welcome to my channel Haute Couture. Today I will walk you through the setup I created for generating haircut textures for real-time hair. I will share my approach to this process along with some tips and tricks to streamline the workflow, making it faster and more efficient. This method is rooted in the classic technique of creating haircut textures in Maya using XGen. Unfortunately, the Maya XGen workflow can be quite unstable and prone to various issues. However, we can follow the same steps in Houdini with much more reliability and peace of mind. Here is my setup. I hope it doesn't look too intimidating. It's actually not that large. I begin by generating the polygon plates that will serve as the surface for growing hair. To do this, I create 1 or 2 lines depending on how I plan to compose the texture. For example, let's say I want to create 3 white strands with varying densities, 3 thinner strands with different densities, 3 flyaway variations. In the second row, I might add a temple hair, 2 variations of baby hair and possibly something like brows or eyelashes. So I need 2 lines that I will sweep to form the polygon plates. These lines are positioned at different levels, one higher and one lower. Next, I need to place points along the curves to match the layout of the future haircuts. For this, I use the Lap Curve Resample by Density tool. By selecting the Constant Interpolation mode, I can adjust the borders of the future haircuts by simply moving the sliders. Alternatively, you could manually place points to create a polyline, but in my experience, this Lap Resample method is much more convenient once you get used to it. For the most precise control, you can create a line using the Add node, like this. However, this approach can be a bit tricky to adjust quickly. For example, if you suddenly decide to add an extra card in a row, you will have to modify all the values, which can be a bit tedious. Next, we merge our rows and pass them through the Convert Line tool to break the lines into separate edges, which will help us create individual plates. I then sweep these lines using an arc, essentially an open circle with a specific radius and angle range, to create a slightly bent geometry. This is just my personal preference. You can also use the Bend node to create a curved surface, but I found that the Sweep node works better for me. Plus, Sweep generates beautiful UV textures, which are essential for applying the hair growth mask later. After that, we use match size to align our plates with the coordinates of the first UV tile. Next, we assign a vertical normal vector to the plates, which is crucial for hair generation. We also create a class attribute based on connectivity to assist us later. Our plates are ready. Now let's talk about the hair card sketch. This sketch serves as the blueprint for generating the hair. While it's often done in Photoshop or similar software, constantly switching environments and creating extra image files can be cumbersome. So I make my sketch directly in Houdini using Texture Mask Paint. I apply this mask to a grid with the UV texture. To ensure the borders of the sketch align perfectly with our future plates, I use the following little trick. I create a helper grid to avoid intersections between neighboring card spaces. As always, when creating images in SOPs, I use a volume. I set the volume's dimensionality, resolution and position, then send it to a volume wrangle node and run a simple code. This code iterates over each point of the plate rows, creating a vertical line of a certain width at each point. You can easily adjust the widths and brightness of these borders if it's needed. Now let's create an elliptical mask for the hair plates. This is a simple task. Just assign the mask attribute with the value of 1 to voxels within a certain radius. Next, we send this mask to a CopNet to convert it into a usable image and blur it slightly. With the mask ready, we move on to the sketch itself. You can notice that I fit the volume data with our card borders into the second input here. I really enjoyed drawing the hair here. I set the paint radius to 0.002. You can adjust the radius using a gesture by pressing Ctrl and Shift and change the painting mode through the circular menu. Once the mask is drawn, we color it and use it to generate guide curves like this. Now I want to explain why I prefer using curves over the guide groom node. I find the guide groom node to be slower and harder to work with. It also caches input geometry, meaning if we change something upstream, it won't update automatically, which is inconvenient in this case. Curves allow us to bypass these issues, and later we can convert them into guides using the guide skin attribute lookup node. But first, let's go over how to create curves properly. There are 3 key things to keep in mind. We need to work in frontal orthogonal projection. The second is that we need to enable polygon snapping mode, and we need to ensure that there is no unnecessary geometry in the space, such as an area light or something like this. If the area light is active, hide it. Now we draw the curves. It's important to start the curve on the plate geometry. This ensures the curve is positioned correctly. If you don't, it will be placed at the 0z axis coordinate, which isn't what we want. Curves that start higher here are placed closer to us, which you can observe from a side view. When correcting curves in perspective view, make sure to turn off snapping. Once I'm satisfied with the curves, I move on. I use the split node to remove the sketch geometry, leaving only the curves, and after that I resample the curves and use the guide skin attribute lookup node to add necessary attribute to use the curves as grooming guides. At this point we have the plates and guides, so we can start grooming. I'll demonstrate this in a separate stream. First, we create a hair generation node. We set the group via the class attribute to isolate a specific surface plate. Then, we adjust the density, influence radius, and other parameters as needed. Here we also add the link to our elliptical texture from the utility CopNet to override the density with the texture. In the Attributes tab, it's crucial to rename the width attribute to p-scale. We do this because we will render the hair using Copernicus, which requires real geometry. We will be using a sweep node downstream, and it uses p-scale to determine the sweeping radius. Once the hair is generated, we add a couple of hair clump nodes for both larger and smaller scale clumps. Next, we use the guide process node. The key modifiers I use here are set length and wave, but I will configure these settings later. After completing the basic grooming, we remove any unnecessary attributes, keeping only p-scale, position, and primitive ID. All of them will help us create different texture maps further downstream. Now we will create a couple of additional attributes needed to bake the anisotropy map. We use orient along curve to add a normal attribute. We can skip the up attribute for now. We resample it if necessary. Then we calculate anisotropy values using a simple vex. An anisotropy map helps us define the direction in which specular reflections move, creating that nice fibrous look. Hair shaders usually include this effect by default, but for hair cards we need to generate it manually. The process of creating anisotropy maps varies depending on the render engine. For example, in Mentor, the direction of specular movement depends on the UV position. Along the x-axis, the value is 0. Against the x-axis, it's 1, and along the y-axis, it's 0.5, a simple float value. In Karma, anisotropy directions are based on the angle around the normal vector, but in principle it's similar to anisotropy in Mantra. Let me show you. Here I've built a simple shader to demonstrate how anisotropy works in Karma. I take the UV coordinate of a texture, extract the vector difference between the center of the tile and this point, and calculate the A102 function value, which falls between minus pi and pi. I then remap these values to a 0 to 1 range. To make this effect more visible, let's put it into a circle and also increase the tiling for better clarity. For the Karma renderer, the vertical upside-down direction corresponds to a value of 0.5, while values of 0.25 and 0.75 direct anisotropy horizontally. When it comes to the tangent map for Unreal Engine, things get a bit more complex. In Unreal Engine, the x direction of anisotropy is determined by the green channel, and the y direction by the red channel. In this wrangle, we create attributes for anisotropy maps for both Karma and Unreal Engine. For Karma, I use the A102 function, while for Unreal Engine, I use the dot product function that we measure for x and y directions of the map. Next, we apply orient along curve to ensure correct sweeping downstream. We can wrap everything into a subnet, like this one. In the group field here, I linked the name of the node with the card number. This allows us to duplicate the node and automatically generate a unique new card each time, or just rename it easily. The final attribute we need is the roughness attribute. I generate this based on the assumption that hair surfaces facing away from the camera appear rougher than those facing towards it. To calculate this value, I measure the dot product between the surface normal and the x-axis in world space. In fact, we can avoid creating this map because many shader systems support the creating Fresnel effect, which is basically the same. With that done, we are ready to move into a CopNet.